G'day everyone, my name's Braden and I'm part of Group 12 with Gil and Michael, and in this video we'll demonstrate the final version of our project, the DriverMate. Before we demonstrate anything, it's important to understand the problem our project intends to solve, and the importance of this problem. The problem we found is that the sirens of emergency vehicles can be difficult to hear while driving, particularly for those that are hard of hearing, and that the flashing lights aren't always visible. If we can solve this problem, we can improve the incident response times for emergency vehicles, reduce the risk on roads for all drivers, and reduce the difficulty curve for hard of hearing learning drivers. Ultimately, the goal of our project is to solve this problem. We achieve this by providing an obvious and clear visual cue for the drivers when an active emergency vehicle is nearby. And our solution to this is the DriverMate. What exactly is the DriverMate? Well, this is what it is. It's a detection and indication system for active emergency vehicles. It provides the visual cue by illuminating LEDs when a siren is detected. You can see these LEDs on the front face of the DriverMate. When installed in a vehicle, the DriverMate is designed to keep vehicle operators more aware on the roads. I'll now hand you over to Gil, who'll talk more about the design of the DriverMate.
Thanks, Braden. In this slide, we have a photo of the DriverMate dismantled so that we can see the individual components. First, audio is captured via a microphone mounted to the outside of the vehicle, and it's transferred to the PCB via a 2-meter screened lead. Next, in block 2, the low amplitude audio signal is amplified to a usable level, and it's filtered via an active low pass filter to remove unwanted frequencies above 2 kHz. In block 3, the analog signal is digitized via the ADC, as the Raspberry Pi has no onboard ADC. Block 4 is the actual Raspberry Pi itself. It samples the digital audio signal at around 9,000 samples per second. It then performs the audio analysis using Fourier transforms to match a siren signal. If 2 consecutive matches are detected, a pulse width modulated output is sent via the current limiting resistors to the LEDs in block 5. Depending on the volume of the siren, either 1, 2, or 3 LEDs will illuminate. Finally, block 6 is a photoresistor, which sends the ambient light level via the ADC to the Raspberry Pi, and that adjusts the LED brightness accordingly, so it puts it into day or night mode. Now to see the DriverMate in action.
In this bench demonstration of the DriverMate, we have a speaker over to the left to simulate sirens and background noise. We have a microphone here connected via a 2-meter cable back to the PCB. On the PCB, we have the filter and the amplification for the microphone signal. We have the ADC performing the translation from analog to digital. We have the current limiting resistors for the pulse width modulated LED outputs. And we have the photoresistor mounted inside the box with a hole out to the top to control the ambient light modes. The Raspberry Pi here is doing the audio processing and output control. It's powered via USB here, and for the purpose of the demonstration, we've got it connected to this screen so that we can see what's going on. So it's displaying the peak frequencies detected, and you can also see that there's no siren detected and that it's in day mode for lighting purposes. So I'll introduce some ambient noise now. And we can see a lot of the frequencies have increased, but we're still not getting a siren detected. If I introduce a siren noise now, you can see that the siren's detected at volume 1 or 2, depending on what the threshold is. As we increase that, we get siren volume 2 and siren volume 3. If we cut the siren, our LEDs go off. So turning the siren back on, we're in day mode, and we can force it into night mode by covering the photoresistor, and the brightness of the LEDs has dimmed, and we're now in night mode. If we come back off, back in day mode, brightness of the LEDs increases.
Thanks, Gil. Hi everyone. I'll be looking at the uses of DriverMate. DriverMate has been primarily designed for hard-hearing individuals and those experiencing some hearing loss from old age. It will provide a visual warning system to alert vehicle operators that emergency vehicles are present. However, with modern vehicles becoming more and more soundproof, all vehicle operators can benefit and are able to use DriverMate. DriverMate has also been designed with a 30-second install or removal time. This allows family members who are sharing a vehicle the ability to quickly remove it should they feel they do not need the device. I will now show a demonstration of a user installing DriverMate. Our user, Gil, has DriverMate in his hand. He enters the vehicle and begins to install DriverMate. Firstly, he mounts the console to the dash using the reusable mounting strip. He then attaches the microphone to the external side of the vehicle using another reusable mounting strip. Finally, he plugs in the USB power supply. You can see here the microphone mounted to the external side of the vehicle. Gil is now ready to commence his journey. Our next scenario is of a person operating a vehicle with DriverMate installed on the dash. An emergency vehicle approaches them and DriverMate alerts them of its presence. This scenario is representative of all vehicle operator users, whether they are hard hearing, have hearing loss from old age, or can hear well. Our user, Michael, is driving down the road listening to music. DriverMate detects a siren before it can be heard from inside the vehicle and alerts Michael. As the sirens on the emergency vehicle get closer, more lights illuminate on DriverMate. Michael has now pulled over while he waits for the emergency vehicle to pass. As the sirens from the emergency vehicle get further away into the distance, lights on DriverMate begin to go out. Once it is safe, Michael pulls back onto the road and continues his journey. Testing was performed on DriverMate to verify the distances for each level of detection, with the typical urbanized area background noise of 70 dBA. Using the distance attenuation for a typical siren sound pressure of 120 dBA, we have matched these results to their corresponding distances shown here on this graph. This test data shows that for distances greater than 100 meters, one LED will illuminate. At distances between 30 to 100 meters, 2 LEDs will illuminate. And at distances less than 30 meters, 3 LEDs will illuminate, showing that the emergency vehicle is very close. Reliability tests were also performed with the worst case scenario of 90 dBA background noise. A siren simulating the minimum acceptable detection range of 100 meters or 80 dBA was played over 100 tests. It was found that DriverMate could detect the siren 99% of the time with 0% false and 1% misdetection. This data shows that DriverMate is very reliable even in the worst case urban noise conditions.
Thanks, Michael. Hi again, everyone. So, as you can see, the design and build of DriverMate ultimately meets the goals that were set for this project, and as a result, we're happy with the outcome. However, as with any project, there's still some limitations and room for improvements. Firstly, our current design only detects the one type of siren, but this can be extended by analyzing other sirens and programming a detection system for this. The response time for siren detection isn't as quick as it could be, and this can be improved by reducing the sampling window size. Since the microphone sits outside the vehicle, it will be subject to wind noise and rain. We need to implement wind braking and waterproofing to the microphone, and retest the DriverMate under these conditions. Currently, the microphone cable is routed through the door seal. This could be improved by implementing a wireless microphone module or even changing the cable to a flat type to improve the performance of the door seal in case of water seepage. Lastly, we could implement data collection functionality for future applications. The data could be direct input from the microphone or readings from other sensors, such as an accelerometer. This data could be used by government bodies for road statistics or vehicle companies for research purposes, as an example. Although we experienced issues with the coronavirus situation that did affect our project, we worked around these issues and continued to build our project to the best of our abilities. The main issues we faced were, the time we could have spent together as a group for designing and building was limited. As a result, most of the code and circuit building was split up and had to be combined remotely. We didn't have access to an oscilloscope or other electronics analysis tools like this, which made it difficult during the building process. Thanks for another successful semester at QUT, as well as a fun project. We hope you like the DriverMate and can see its potential for vehicle-related safety applications.